right, so let's come back to our differential gene expression analysis. So recall that in our previous lectures, we spent quite some time to talk about the high-level formulation, or including the basics, the foundations like the frequentist statistic versus the Bayesian statistics, and what is the p-value under the frequentist statistics, and what's the Bayes factor under the Bayesian statistics, right? So we spent quite some time talking about those. And today and next, we talk about the specific t-test, which everybody have learned this at least to some extent before. So let's try to revisit the key assumption of the t-statistic. So which is that, I think for the origin, so the original formulation has that the x1 to xm, let me put it here, sorry, let me change to a different pen. So the original formulation, I'll just write it here, has this idealistic assumption that is x1 to xm. So this is one gene's m measurements, observations under one condition, are IID following a normal distribution with mean mu x, variance sigma square, okay? And another sample, y1 to ym, is the same gene's n measurements or observations under condition 2 are assumed to be IID, also normal, mean as mu y, and variance same as before. So they share the common variance. And of course, the two samples, they are independent. So usually we use this perpendicular sign to mean or to mean independence, okay? So they are independent. So this is the original formulation. So with this, then everything can be derived. So just as I said, the test is to address this hypothesis or to test this hypothesis that mu x equals to mu y. That's the null hypothesis. And therefore, the natural statistic would be to use an estimator from mu x minus an estimator from mu y and see if this estimator is close to 0. So a natural estimator would be the average of the x's as x bar and the average of the y's as y bar. So that difference is our statistic, right? And we want to know what's its null distribution under the null hypothesis. And unfortunately, this distribution under this normal assumption would have this unknown parameter sigma square involved. So to address this issue, our idea is to move this quantity to the left-hand side so the right-hand side becomes a standard normal distribution, okay? With that, the sigma goes to the left-hand side. But we still need to find an estimator so that we can calculate the number to put here from the data. So that gave us this, we use the so-called pooled sample variance, which is from pooling the sample variance of the X sample and the Y sample, and they are pooled into this SP square by this weighted sum, and the weights are actually determined by the sample sizes. Okay, so we talk about this whole idea and then put it here. We said that under this normality assumption, this will follow a T distribution, which has degree of freedom as m plus n minus 2. So I said T distribution is an arbitrary, it's a constructed distribution for the purpose of doing this test. So it's just nice that it doesn't have any unknown parameters, just this degree of freedom. And this degree of freedom can be known when our two sample sizes are known. So this is very nice. So that's why in the pre-computer age, the statisticians at that time, they will spend a lot of efforts to do manual calculation for the quantiles and the tail probabilities for this distribution. And once they have that table, then any users can just look up, so based on the T statistic number, the realization of this, right? Whatever number they have for the sample they collected, they put this number into the table to look up the corresponding probability and call that the p-value. So that was the old practice. And so in the last lecture, I didn't emphasize too much about this normal assumption. The reason is that although this is the theoretical foundation for the whole derivation, but because of the central limit theorem, even though our sample may not be from a normal distribution, but as long as it has finite second moment, we can use the central limit theorem to say the X bar is still approximately normal, the Y bar is approximately normal. So the whole idea still follows. But one thing you may wonder is it safe to assume the same variance, the same population variance for the two conditions? This is a really hard thing to check, especially if your M and N, the two sample sizes are small. So for example, if we only have 3 and 3 replicates under each condition, then how can we verify the variance, right? Using small number, 3 numbers, compute the variance is possible, but we know it has a large uncertainty. So that's why so today we are going to focus on 2 topics from here. One is that when M and N are both too small, we know this SP square, okay, even under this common variance assumption, we know this SP square is a poor, or it's a valid estimator of sigma square, but it may not be good because itself may have a big variance. So by big variance here, what I mean is that if you collect the samples again, you do another experiment, and you can compute another realization of SP square, and then those 2 realizations may differ quite a lot. So that's not good, right? So in this case, how can we stabilize our pool sample variance so that its variance is not so big? So that's the question we want to answer. And when we will show that using the Bayesian framework, by assuming sigma square follows some prior, then the resulting Bayesian estimate would have smaller variance than this SP square, even though that estimator will have a bigger bias. So we will show that later. That's the first direction to address the sample size issue. Another direction is that maybe some of you have heard of this. There's another version of t-test called the Welch's t-test. So that one is different from this one by not assuming the common variance. So I'll start from there first. So let's first talk about this Welch's t-test. So to make it more specific, this name may not look familiar. We'll just call it Welch's unequal variance t-test. Okay, it's still to compare the 2 samples, but its assumption is more relaxed. So here we are assuming, again, 2 independent samples, x1 to xm, IID from normal, mean mu x. The variance, let's denote that sigma x squared. So it carries this x, and y1 to yn, IID, normal, mean mu y, variance sigma y squared. So we are no longer assuming sigma x squared and sigma y squared to be equal. Okay, so in this case, we are still trying to standardize, this statistic we are interested in, x bar minus y bar, right? But how do we standardize it? What's its variance? So under the assumption that these 2 samples are independent, we can easily derive that variance of x bar minus y bar would be equal to variance of x bar plus the variance of y bar, right? We know this. And then for the variance of x bar, we know it's equal to, so I'm basically assuming a lot of basic mathematical statistics without deriving everything, but I'm just giving you the result. And so here the sample size is a known fact is that this variance of the average of the sample mean is equal to the variance of each xi divided by the sample size. So this is equal to sigma x squared over m. And the variance of y bar is equal to sigma y squared over m. Okay, so this is something actually my other undergraduate class 100B will cover. But here I'm just using the result. Okay, so with this variance, then to estimate this variance, right? We know this involves unknown sigma x squared, sigma y squared. So a natural estimator of this, so we want to estimate this by using our sample variance. So we just put our Sx squared, whose formula is right here. This is our Sx squared. This is our Sy squared. We use them as the estimators of sigma x squared and sigma y squared. Okay, so we have that. So in order to standardize x, and this is the variance, right? We estimate the variance. And then to standardize x bar minus y bar, we just put in the estimated standard deviation of it. So that will be the square root of this. And that's Sx squared over m plus Sy squared over n. Okay. This is the test statistic for the Welch's t-test. So we no longer assume the two distributions have the same variance, but we estimate their variances separately. So it's like a separate variance approach. Then the question is, what is the null distribution of this test statistic? So it's not as clean as the two-sample t-test, whose null distribution, which we have seen here, is just the t-distribution with this degree of freedom, which is very nice. Here, actually, we can show that under the null, it also follows some t-statistic, but the degree of freedom is a lot more complicated. Okay, so I will leave it here. So it's a quite complex thing. And the Welch make a very big contribution for deriving this degree of freedom, which I can quickly show you the wiki page so you can get a sense of what it looks like. Okay, so give me 1 second. All right, this is the wiki page for the Welch's test. Let's scroll down. This is the degree of freedom for the t distribution. So basically, they call it S1 squared, we call it Sx squared. They call S2 squared, we call Sy squared. And their N1 is Rm, their N2 is Rm. So that's it, okay? And so this S1 fourth is just the square of S1 squared. So you see, that's the formula for approximating the degree of freedom in the t distribution for this Welch's t-test, okay? So I will ask you this question first. Do you think it's better to use this Welch's t-test or the two-sample t-test if I give you two sets of numbers to compare to run the t-test? Which one would you pick?
Doesn't it depend on the number of samples in each distribution?
Of course. Then what's your decision then? If the sample size is small, which one would you use?
If the sample size is small, wouldn't we use Welch's test?
Why is that?
Because I think it says that you want to use the Welch's test when there are unequal or very skewed sample measures. So that might account for the error in that.
And so where did you find this statement, may I ask?
I think it's on the wiki page. It says Welch's t-test is done for unequal population variances. So I'm assuming if the population is small, or if there's a large imbalance in the sample sizes.
Right. So Wikipedia says it should be used when the sample size is unequal, right? Or when you believe the population variances are different. But how is this related to the sample sizes of the two samples? I mean, let's say m equals 3, n equals 3. So it's balanced, okay? Versus when m equals 10, n equals 10, 10 versus 10 is still balanced. So we're not really reaching this unbalanced sample size issue when mentioned by Wiki. I'm just saying, let's assume the balance scenario. Would you prefer the two-sample t-test or Welch's t-test when the sample size is small?
Wouldn't you still prefer Welch's even if the sample size is small, because you don't necessarily know the actual population variance overall. Like, you're just estimating it from the sample, and if the sample size is small, then then the distribution of possible variances that you can get would be pretty wide. So the Welch's test allows for that wider variance to possibly be accounted for.
then, okay. So I assume that here there's a reverse of logic, okay, in your description or statement. Let me just try to disentangle that. Is there saying that when the sample size is small, then the population variance can have a wide range of values to take? That's what you said, right?
I may have said that, but I meant to say like the estimated variance that you get from the sample size will
It's
be
yeah.
yeah, will be much bigger if the distribution will be much wider when the sample size is smaller.
Right, exactly. But basically that only says that you can hardly tell whether the population variances are equal or not, right?
Right.
Right. So let's say if you have m and n equals 3, and sx squared in our notation say is 2, sy squared is 4, right? They look very different. But in this case, the population variances could still be same because the sample variances have very big variance, right?
Mhm.
Yeah. So I would say this is a trade-off. But given your argument, then you may wonder a question. Why is the two-sample t-test still so popular, even more popular than the Welch's test, right? If that's the case, then we should just teach you the Welch's test and completely forget about the two-sample t-test.
I mean, at some point, I guess on a purely operational note, like the two-sample t-test is good enough, in particular if you don't want to deal with like the the calculating of degrees of freedom for that. I mean, that's the only argument that I could come up with right now.
Okay, but yeah, okay, so so you say the degrees of freedom here, right? This one's very complex.
Mhm.
Yeah, but the thing is that now with the computer, I mean this one, with the computer, this computation is not really nothing. It's really nothing, right? So we don't have to compute it by hand. Yeah, I agree. In the old days, the t-test has an advantage because we can just put in the degree of freedom as m plus n minus 2. That's easy, but this one requires additional computation. But now with the computer, do we still care about this? Or I'm curious about what you think. So what other people think. You can all tell me your thoughts. Any advocates for t-test, for two-sample t-test? I would say, even though this is I would say those two tests are so classical, right? But this question is universal. Like when we do real data analysis, among many methods, which one do we pick? What is our justification? Any other opinions? And thank you, Tim, for offering your thoughts. That's great. Okay, so if there are no more opinions said here, I will just say my own thoughts. Okay, I feel like, in my opinion, if you have, so I think this equal variance versus unequal variance judgment has to rely on some domain knowledge. So when you know the measurement of your instrument, right, like the machine you use to generate data, you must have some understanding about whether the measurement uncertainty, the measurement randomness is the same under two conditions. So if you have that belief in your equipment, then why not using a two-sample t-test, right? So that can give you one fewer parameter to estimate. And to me, that's an advantage. But if you are just having some observational data for which you have no much understanding about the generation process, so in that case, it's not safe to simply assume that the two conditions have the same variance, then you should use the Welch's t-test. That's one thing. And another thing I think which is very interesting is about whether we can add a test before running this Welch's test or two-sample t-test to test whether the two populations have the same variance or not, which is the thing I want to introduce here. So this is called the F test. So I'll stop sharing this one and I'll share my handwriting. So which is called the F test. So the F test is a way to test if the two samples will support the null hypothesis that the two normal distributions have the same variance. Okay, so for the F test, still under the same Gaussian normal distribution assumption as we have in the Welch's t-test. Now, but the null hypothesis is that we are testing sigma x squared equals sigma y squared, while the alternative is that sigma x squared doesn't equal sigma y squared. Okay, so here the Gaussian normal distribution assumption is really helpful because with that assumption, we can have this F statistic, which is just constructed by the ratio of the two sample variances. So Sx squared divided by Sy squared. So in other words, if this ratio is too much larger than 1 or too smaller than 1, we would want to reject the null. Otherwise, we want to not reject the null. So basically, that's the whole decision. And for this distribution, for this ratio, under the null that the two population variances are equal, we also have an arbitrary distribution. Our founders of statistics derived for it. It's called F distribution. And F distribution will take 2 degrees of freedom, one for the numerator, one for the denominator. For the numerator, it's m minus 1, sample size minus 1. For the denominator, it's m minus 1, another sample size minus 1. So the F distribution would take a form like this. So for this ratio, we know its value cannot be negative, right? So the distribution of the F distribution has domain just in the positive part of the real line. And so if we plot the density, okay, so this is like a density function of this F distribution. I'm just making an arbitrary shape, but it usually takes a form like this. So the shape depends on the 2 degrees of freedom, but it's something like this. So therefore, when you want to make a rejection, you will need to calculate the p-value, right? And compare it against your significance level. So let's say your significance level alpha, let's say, for example, 0.05. That's the one we use a lot, right? How do you compute a p-value based on the observed value, the realization of this F? Let's say, what if this ratio takes value 1.5, let's say, in our sample? So in this case, because under the null, okay, under the null, the ratio should be very close to 1. So in this case, what we will do, let's say 1 is right here, then you will pick 1.5, okay, I'll just put it here, as one cutoff based on your realization. Another cutoff to the left of 1 would be 1 over 1.5. You take its inverse. And then you pick those two values and you take the corresponding right tail and the left tail probabilities and add them up. That's the p-value for running this test. So in other words, because the alternative hypothesis is two-sided, then we want to make the rejection whenever the ratio is too big or the ratio is too small. Okay, and I'm skipping the technical detail about why we should take the inverse. But the quick thing to say is that, also, I will cover this in my other class. Maybe this is like an ad. But what I will say is that, so when we have a random variable, I call it x, if x follows, say, n minus 1 distribution, a fact we know is that the inverse of x would follow f n minus 1 distribution. That's a very interesting fact. So the inverse still follows F distribution, but you have to swap the 2 degrees of freedom. Okay, so this is the F test, right? This is just one way, the most simple way to test if the two populations have the same variance. Then a natural question I think people would say is that, how about I just do the F test first, see if I reject the null. If I don't reject, I will do 2-sample t-test. If I reject the null, I will do the 2-sample, or I will do the Welch's t-test. Would that be a good idea? And any thoughts on this? Maybe we can do, people who agree with this approach, you can just raise your hands. We'll see how many people agree with this is a good idea. Could just do 2 steps. Okay, Guanglao raised his hand. Only one. And 1 clap. Okay. More people. We have actually been, except me, we have 28 here. But let me see how many hands we have. 7. Okay, so only a small proportion. So anyone who, okay, more. Now 9, 10, any more? We can ask people from both sides to say their justifications. 11. Okay, 1 people put a hand down, so 10. Seems like debating. Okay, but the hands are down. So anyone who didn't raise the hand want to say why? Say your justification. Or if you're unsure, you can also say why you are not sure.
Well, I think we may encounter some problem of double dipping. We may use our data twice, so we may cause some problem.
Okay,
that's why I
true.
don't agree.
Yeah. Okay, yeah, Zhiqian made a very good point, right? This is something I want everybody to have this caution. So whenever we use the same data for twice and only use the result from our last step, like the p-value or anything about statistical inference, okay? We talk about p-value or confidence intervals or like the Bayesian framework, like Bayes factor, for those kind of things related to uncertainty. If we have other steps before this that touches this, that have touched this data, then it's always good to have that warning in our mind. Maybe the previous steps would actually affect the result of the last step. So I think Zhiqian made a very nice point. And actually, for those who think this is a good approach, anyone who wants to give a justification? If you just think it's intuitive, that's a justification as well.
Yeah, I think it's intuitive to first do the F test to test the variance if they are equal between the 2 samples, and then you do the second step to test the mean, whether they are the same. I also wonder, do we need to test the normality because we have this assumption, right? Yeah.
Right. So you raise a very good point, right? The normal assumption is right there, but now the things can become very complicated. Wow. So right, if basically, this is something I want to tell everybody. So basically, the controversy here, I think in general, in statistical, the whole idea of doing statistical inference is that if you have a small sample size, okay, maybe let me say this way. So the sample size, by using my analogy, is like your budget, okay? And the model complexity is like the price, the cost or something you want to buy. So there needs to be a match, okay? So in other words, if you have a very small sample size, you don't want to train or fit a too complicated model. So because you just have some small points, right? So let me just give you one very simple example. Let's say that we do linear regression, okay? And this is our X, this is our Y, and we only have 3 points. So in this case, your only solution for fitting a regression line would be linear regression, right? You cannot do anything else because if you assume there might be some noise in your measurements, then if you do anything beyond the linear regression, this line is badly drawn. Anyway, so I'll just add point here. So, but anyway, with that, if you fit a complex model, you are likely overfitting to this data. Intuitively, you will guess that, right? And then that model may not be useful. So usually when we have a small budget, we can only buy a simple thing, a cheap thing. So simpler model match with small sample size. But on the other hand, So small sample size go with simple model. Okay, they go hand in hand. But another problem is that usually the small model, simple model, small sample size, simple model has stronger assumptions. So like in our case, normal assumption, okay? Or like in the linear model case, we assume the errors, so the vertical errors are following a normal distribution. So in those cases, the stronger assumptions cannot be checked if your sample size is so small. Because with 3 points, how can you tell whether they are from a normal distribution or not? You cannot, right? So that's the, I would say this is a dilemma or something we cannot ever overcome. So the good thing about more complex model, for example, non-parametric regression, kernel density estimation, or even neural network right nowadays, is that they don't have any specific parametric form of assumption. Like when you do neural network training, you're not assuming the function to be any specific form. It can be very, very complex. But you need a really large sample size to support that complex model, right? So in other words, trying to get rid of assumptions require a lot of data. But when you only have a small sample size, you have to use the assumption to help you. And this assumption plays sort of like the prior role in Bayesian statistics. It's your belief. You use your own belief to make the data useful. Otherwise, the data is just useless. So I hope this whole argument can make people realize how subjective statistical inference is. We have to acknowledge that. So that's why if I give you the same real data set for you to analyze, I think you may come up with different strategies and give me different inference results. And that's okay. And that's unavoidable, but you have to justify the results. And hopefully, our scientific conclusions will stay stable or robust regardless of the inferential procedures. That's the hope. Okay, so if you realize that, then you will see the job of statisticians can hardly be replaced by AI, I would say, because there are so many decisions involved and it's not a pipeline. So coming back to the question we discussed, is it okay to use the F-test before the Welch's test or the two-sample t-test? Actually, if you are sharp enough, if you have sharp eyes, the wiki gave us the answer. Wiki give the recommendation, and I checked it out myself. I think it's very interesting. So here it says that it's not recommended to pre-test for equal variance and then choose between t-test or Welch's test. Okay, so but the reason is in this reference. Okay, let's click here. Okay, this is the paper. I will give you the paper on UCLA. So because UCLA has the access. So the reason is, so basically this is not a theoretical paper, but it has a lot of numerical results. And the numerical results actually confirmed what Zhiqian was saying about the so-called double dipping issue. So you can see here, simulations disclose that the two-stage procedure fails to protect the significance level and usually makes the situation worse. So why would that happen? The reason, I think the underlying reason we must realize is that no test is perfect, right? So we know there is a type 1 error. Type 1 error means that even though the null is true, you still have a chance to reject it, right? Or the significance level is for that. 5% significance level means that when the data are indeed from the null, you still have 5% of the chance to reject the null. So in that case, this type 1 error, whatever error you made in the first test will go to the second test. So therefore, the actual type 1 error, type 2 error of the entire procedure, the entire two-stage procedure is not just the type 1 error of your second step. In the second test, when you say, I do the Welch's test, I'm conditional on the first test, right? But what you care about is the overall, the entire procedure. So that's why there's no guarantee that using a pretest will really help. So I know this is counterintuitive, but if we want to be rigorous, that's the problem. So I would say here, maybe we can quickly go to the paper. Okay. Go to the conclusion. It's a very short paper, by the way, so people can read it quickly. So go to the conclusion. Practical recommendations. Can you guys see clearly? Okay, although many current textbooks state that preliminary tests are no longer favored and not really necessary, many researchers in psychology, so this is a psychology journal, education, other social sciences are unaware of the serious disadvantages of these tests. Current recommendations do not convey the message that they substantially modify the significance level. All findings in the present note, this paper, suggest that researchers should pay more attention to differences in sample sizes as a danger signal rather than to heterogeneity of variance. I think this is a practical recommendation because, as I said, whether the population differences are equal or not is unknown. It's not observable. But the sample size unbalance is clear, right? We know the sample sizes. So basically says that you may choose the Welch's test if the two samples have very unbalanced sizes. And one should also keep in mind that differences or lack of differences between sample variances do not necessarily correspond to population parameters. This is what Tim said. In other words, if the variances of sample values are nearly equal or differ only slightly, it is still possible for population variances to differ to a large extent. As can be seen from figure 1, we'll see that later. Slight differences in population standard deviations have large effects if the ends of two treatment groups are unequal. Okay, let's go there, figure 1. Right. So basically, this is the ratio, okay, of the two population standard deviations, sigma 1 over sigma 2. So basically, I think this is about type 1 error rates of unconditional student t-test, unconditional Welch's t-test, and choice of test conditional on outcome of a preliminary Levine test. This is also for testing the equality of variance, similar to the F-test, as a function of ratio of population standard deviations. Top, large standard deviation associated with larger sample size. Bottom, larger standard deviation associated with smaller sample size. But anyway, so you know here, because the probability of rejecting the null should be 0.05. And if you have this thing lying above the horizontal line, it means that you fail to control the type of error. Okay, so basically, you can see that even though, so basically for the samples, this is the ratio of the standard deviation, and you can see that the t-test doesn't work, okay? The Welch's test works well, and the conditional one doesn't work that well. And this is another way. So basically in both ways, the sample sizes, because I think the simulation, are associated with the ratio. So the sample size is unbalanced, you can see. This is sample size 40, 20, 20, 40. So it's unbalanced. So clearly this figure shows that you want to use Welch's t for the sample size like this. Anyway, so coming back here, furthermore, oh, maybe here. So this means that the significance level of a test can be inaccurate even when sample variances appear to be nearly the same. Furthermore, the largest inaccuracy results when the disparity is slight rather than extreme, and it is more difficult to rule out slight population differences from sample data. So next sentence will make more sense. In practice, researchers may be tempted to improve results by making the alpha level of a preliminary test more stringent, which means if you may want to make the F test more stringent, that means you are very unlikely to reject a null, okay? I think that's the result. But this procedure we have seen is counterproductive. Increasing sample size helps to a certain extent, but not much, as shown in table 1. When sample sizes are unequal, it appears that the most efficient strategy is to perform the Welch's t-test or related separate variances test unconditionally without regard to the variability of sample values. So to summarize, this one is saying that you should tend to use Welch's test if you have any doubt. So because it's just safer. I think that's the recommendation from this paper. But as I said, I still believe that the two-sample t-test has its value because it has one less parameter. So based on my own logic, for our biological data, if like RNA-seq data, if you only have 3 replicates, right? In that case, I would say I would prefer smaller number of parameters. So that's just my own philosophy. But again, I would say this is everything, you know, about statistics, method choices. It's not black and white, or it's not 0-1. So there's always some subjectiveness involved. All right, so that's about the Welch's t-test and the two-sample t-test, and also we talked about the f-test in the middle. Do we have questions before I talk about the next thing? How do we use the Bayesian idea to help us achieve a more stable estimator if our sample sizes are too small?
I have a question. When you talk about unequal sample sizes, like what's like the standard for unequal? Like how different does the sample size have to be considered like there's like a big difference?
That's a very good question. So that's why I think maybe you should read that paper. In that paper, it has a lot of numerical results, and you can see when the result of the t-test starts to deteriorate. So you may see that, but I would say that's also subjective. Like in that case, maybe people will say 40-20 are unequal, but how about 30-20? How about 25-20, right?
Oh,
Yeah. So I would say maybe the best answer I can give you is that that's the power of simulation. Try to do simulation yourself and see, because in a simulation, you know the truth, right? So then you can verify whether the type 1 error is controlled. What's the power?
Okay, great. Thank you.
Thank you. Okay, so let's talk about the Bayesian. Okay, so still under the framework, now let's come back to the two-sample t-test framework. Okay, so we still have x1 to xm. Now back to the common variance scenario. Okay, and independent with y1 to yn, IID normal, mean, max, mu y, sigma squared. Okay, in this setting, now we define that as pooled sample variance. So SP squared. Okay, for this one, I'm not going to write down the formula again, but it was in our previous notes. So we know actually about the distribution of this SP squared. So the distribution is actually very nice. So the distribution is that if we multiply this SP squared by a ratio, m plus m minus 2 in the numerator divided by this common unknown sigma squared. So this term actually under our mathematical statistics theory follows a chi-square distribution with the degree of freedom as m plus m minus 2. So this is something we know. Okay, and chi-square distribution has some nice properties, which is that its mean and its variance are directly related to the degree of freedom. So that says we know the expectation of this ratio is the mean of the chi-square, right? So it's just the degree of freedom. This is it. And for the variance, it's 2 times the degree of freedom. Okay, so those are known results. But then how about the variance of SP squared? We can use this to derive it. So we know that once we get this coefficient out, we need to square the coefficient, right? And then we can move it to the right-hand side. So basically, this will tell us the variance of SP squared alone would be equal to 2 times sigma the fourth, divided by m plus m minus 2. Okay, I have the square here and one numerator. They cancel each other because I said this gets out will be square. But this variance itself is meaningful. You can see that it's inversely proportional to the sample size. The larger the sample size, the smaller the variance. The smaller the sample size, the larger the variance. So that's why when n plus n is only equal to 6, you see, n equals to 3. That's the common scenario. So it's this. Okay. And then you can see if the population variance is big, this can be very big. So that's why we would want to stabilize it by finding a better estimator that has a smaller variance. That's the goal. So how to improve the variance of SP square by constructing a new estimator. Okay, so this is a practical reason for using Bayesian here. We are not like let me see. We are not really like that kind of Bayesian believer that we use Bayesian because we believe it's more reasonable. But here is a practical reason. Sample size is too small. So prior can be a supplement to the data, to the sample size. Okay, so to do that, you know the Bayesian framework, and here the parameter is sigma square, right? Sigma square is our parameter of interest. So as I said, in the Bayesian framework, our target is the posterior. So we want to obtain the posterior distribution of sigma square given our data. Okay, that's what we want. And now the data, all the data information about sigma square, right? All the information in my x1 to xn, y1 to yn that can help me inform sigma square is in the SP square. So SP square is just a data summary that carries all the information about the sigma square. So in this case, I can assume that I will put this posterior as this. Okay, so in other words, I use SP square to represent my data. Okay, then how to derive this? Based on the Bayes rule, we know, and this p, small p, I mean the density function. Okay, it's proportional to the density of SP square conditioned on sigma square times the prior density of sigma square, right? That's by the Bayes rule. Okay, and for this term, we know how to derive it. This can be derived, this density can be derived based on this distribution. So this can be based on the distribution n plus n minus 2 over sigma square times SP square follows chi square m plus n minus 2. Okay, this is from that distribution we assumed. How about this one? This prior needs to be specified by ourselves. And now I'm going to introduce a very fundamental basic concept in Bayesian statistics called the conjugate prior. Okay, conjugate prior, here we are using the parameter sigma square as our example. Conjugate prior is defined as the prior so that the posterior and the prior belongs to the same distribution family. Okay, so P sigma square such that P sigma square given this SP square, the posterior belongs to the same distribution family. So by distribution family, I mean if the prior is normal distribution, we hope this posterior remains a normal distribution. And if it's exponential distribution, this is still exponential. If this is gamma, this is still gamma. By the way, exponential is a special case of gamma. So that's the definition of posterior. So you know that to really make this happen, right? Mathematically, look at this relation. We really need the prior to have some terms to have the common terms involved in this term. This is what we call the likelihood, right? This likelihood function, likelihood function, it's a function of the parameter sigma square, but it's defined as the density of data given a parameter. I'll write it here. So the likelihood of sigma square, okay, is defined to be the density of SP square conditional on sigma square. So in other words, even though a lot of people use the term loosely to say, oh, likelihood is the density, but I want to make it clear that these two functions, likelihood function and density function, actually have different arguments, okay? The likelihood function's argument is the parameter value, while the density function's argument is the value of this random estimator. So that's why by nature, they are different. Although it's defined in this way, okay, it's defined in this way, but here sigma square is put under the conditional, here is the argument. Anyway, so this is a technical thing, but coming back here, given that we can write down this likelihood, maybe I'll just do it. Okay, so the likelihood, I'll try to simplify the notations a little bit, and things are in the details are in the notes I will post. So by the way, so given this, let's just write this first. Okay, so let me simplify this term, m plus 1 minus 2. Let's call it d, okay, because it's a long term, call this d. Then we can simplify this density, I'll say proportional to. So by writing this large proportional to, I mean, I ignore a lot of constants. I only keep the sigma square term and SP square term. So anything else can be ignored, the constants. So this is proportional to d times SP square over sigma square to the power d over 2 minus 1. This is based on the chi-square distribution density, by the way, times exponential to the negative d times SP square divided by 2 times sigma square. Okay, that's the density of this is the density of SP square given sigma square, also the likelihood of sigma square. So to find the conjugate prior, okay, so that combining them, the product, the posterior, will still belong to the same distributional family as the prior. You would immediately know that the prior must have terms that can be combined with the terms in the likelihood, so that after we do the combination, in terms of the function of sigma square, it stays the same. So for here, in the likelihood, sigma square appears in power, right? This sigma to the negative 2 times this term. That's the power term of sigma square. And here is the sigma square is in the denominator of some exponential function. So therefore, to find the prior of sigma square, we also need a term about sigma square to the something here, and we need an exponential term with sigma square in the denominator here. Okay, so that's some prior we are looking for to satisfy the conjugate prior requirement. Unfortunately, there is such a prior, and it's called the inverse chi-square. And actually, if you go to Wikipedia page and find the conjugate prior, there's a table it will give you for whatever likelihood was the conjugate prior. So you can look it up there. And this is the most convenient way of doing Bayesian statistics, because you make the conjugate prior to be some common distribution, and the posterior stays as in that common distribution. So anything about the posterior afterwards will be easy. Okay, so now let's say that we would assume the conjugate prior based on this likelihood form. So let's say we assume sigma square, its own distribution follows some distribution called inverse chi-square, okay? And this inverse chi-square involves 2 parameters. I think it can be also called inverse gamma, but either one would work. Okay, V and S0 square. Okay, so it has two parameters in the prior. And in the Bayesian statistic, we call those prior parameters as hyperparameters often. Okay, so under this distribution, the corresponding prior density would take this form. Again, I'm writing proportional for simplicity. Sigma squared to the negative v over 2 minus 1 times exponential to the negative v times s0 squared over 2 sigma squared. Okay, now use your eyes to compare the terms and recognize the similarity. So as I said, this is the power term for sigma squared. This is an exponential term with sigma squared in the denominator. So they are very similar, right? So therefore, that's where algebra is really useful, basic algebra. Then you can recognize which terms you can combine. So then I would know this should be combined with this. This should be combined with this, right? So then the posterior, of course, p sigma squared given as p squared would be proportional by to their product, right? And by combining their product, I will just write it. Sigma squared to the negative, okay, d plus v over 2. Let me see. Minus 1. Yep. Right. V plus d plus v over 2 for sure. I will have a plus minus 1. Yep, minus 1 and minus 1. Correct. That should be correct because I have 2 minus 1 here. Minus 2, my bad. So I put one of them into the ratio so I can keep the minus 1 here. The reason I want to keep this minus 1 is because I want to say, with this prior inverse gamma, inverse chi-square distribution, the posterior still belongs to inverse chi-square. So I need to know what's the corresponding two parameters of the posterior inverse chi-square. Okay, that's the sigma square term, exponential term. So this one is a combination. So basically, we can write this. So negative, okay, d times sp squared plus v times s0 squared over 2 sigma squared. Okay, so now we need to recognize what's the posterior distribution. So seeing here the density and its relation to the parameterization of inverse chi-square, you know, the first parameter v goes here. The second parameter s0 squared goes here. So correspondingly, you know, we can tell that based on this parameterization, this new v should be, the new v for the first parameter should be d plus v minus 2, right? That should be the first parameter for the inverse chi-square by comparing this to this. No. Okay, and now I know the numerator, by ignoring the negative sign, the numerator of the exponential function should be equal to the product of the two parameters of inverse chi-square. So I know this. Then I know the second parameter should be equal to this divided by this, right? So then it should be equal to dsp squared plus vs0 squared divided by d plus v minus 2. Okay. So this is how we do the conjugate prior in Bayesian statistics. We recognize what's the two parameters for this inverse chi-square. That's our posterior. You may wonder why we need to do this. The reason is that once we know the two parameters of the inverse chi-square, we can use known properties of this distribution, like what's its expectation. That's what we need. So we don't need to do the expectation of sigma squared given sp squared by doing integration by hand. We can just use known property of this distribution. That's the only purpose. Okay, so finally, the expectation actually is s0 squared. So basically, this property of this parameterization is that expectation of sigma square is S0 squared. So going to the posterior, let me see, sorry, let me try to number my page. Okay, going to the posterior, I would have expectation of sigma square given as p squared equals to this term, So dsp squared plus v s0 squared divided by d plus v minus 2. Okay, so what's the implication of here? Let me take another piece of paper. So the implication is actually very interesting. And I think that's a nice thing for Bayesian statistics. So the implication here is that if you believe, or if you remember, D is the total sample size minus 2, right? This is what we have. Going here, the m plus n minus 2. So D is the degree of freedom from our data, from our sample. While this V is the first parameter in our prior inverse chi-square. And this V is also playing a similar role as that degree of freedom thing. Okay, it's playing a similar role. And SP square is what we estimate from data, pool sample variance, while S0 square is the expectation of sigma square under the prior, which means that if you don't see data, if you just want to guess a value for sigma square, you would guess S0 square. Okay, so therefore, if you think D plus V can be much larger than 2, which can be possible because V is something we can specify in the prior. Okay, in this case, we can say that this minus 2 in the denominator can be ignored. Then this posterior expectation, so that's what you expect for sigma square after seeing your data, that's the posterior, can be written after ignoring the 2 as a weighted sum. So become D over D plus V times SP square plus V over D plus V times S0 square. It can become a weighted sum of your data's estimated pooled sample variance and the prior expected variance, right? Prior expected variance of sigma square. Sorry, the prior expected sigma square. Yeah. So it's a weighted sum of that. So basically, you are using your prior knowledge to supplement your data. So this is a very straightforward way to see what the nature of the Bayes estimator is. Okay, so is everybody clear up to this point? And I would say this is not just this one example. A lot of those Bayesian estimates have this nice decomposition. It can be written as something from your data plus something from your prior. And this is the nice thing about using conjugate prior, by the way. Okay, so questions are welcome anytime. And so if not, then I will move on to talk about one last point. That is, how do we know if this thing is having reduced variance, right? So that's our original purpose. Don't forget about this. So if we use this as our new estimator, then what's the variance? Okay, the variance of this thing, dsp squared plus vs0 squared divided by d plus b minus 2. Is its variance really smaller than the variance of our sp squared? Okay, so now for the prior parameter s0 squared, let's assume that it's known, it's given. So it's not from our data, and so it's not random. So in this case, we know when we calculate variance, anything added to it, but it's not random, can be ignored, right? So the variance is basically equal to just the variance of d sp squared over d plus v minus 2. It's just that. And then it's just getting out d over d plus v minus 2 squared times variance of SP squared. Now it should be clear to you why we reduce the variance, because this term is can be made less than 1 if we set V to be greater than 2, right? And V is something we should set ourselves. So that's possible. So therefore, we reduce the variance in this sense. So make the variance smaller. How about the bias? So we know that there's always a trade-off, and we know that the expectation of SP squared is equal to just sigma squared, which can also be seen from here. You see, this relationship is from the property of the chi-square distribution, but if you simplify it, expectation of SP squared is sigma squared. So it's unbiased, okay? This says that SP squared is an unbiased estimator of sigma squared, which is nice, although it has a large variance. How about the expectation of this new estimator? Okay, how about this new estimator? Then clearly SP squared is the only random variable, okay, here in this consideration. Then we should be able to write it just as sigma squared plus V as 0 squared, D plus V minus 2, right? So unless this can only be written as approximately sigma squared if you have this D plus V much larger than 2. So minus 2 can be ignored, and also S0 squared is equal to sigma squared, right? So it can only happen when those two things both happen, but not really guaranteed. So in terms of the bias, this one cannot beat the original pool sample variance. But what's gained clearly is the variance. So you have strong motivation to set this V to be large to really reduce the variance in your prior, right? Because this V is kind of equivalent to the degree of freedom, which corresponds to the sample size in your prior. So if you want to set that degree of freedom large in the prior, it can counteract the small sample size you have in your data. Okay, so you can see this trade-off, right? Going Bayesian can stabilize the variance, but introduce potential bias. Okay, so one last thing I want to say is about the choice of V and CS squared, right? So V is actually maybe easier, as I said. You have tendency to set it big. How about S0 squared? We want it to be close to sigma squared, but sigma squared itself is unknown. So that's the challenge. We cannot really counteract that. So to address this issue, one way to set this S0 square is to use what I mentioned before, empirical Bayes. Okay, so on the high level, the idea is to use what we called the marginal likelihood. Okay, so what's the marginal likelihood? So our likelihood, if you recall, and as I said, we can write as L sigma squared, okay? It's defined as the density function of SP squared given sigma squared, given the data. So how about now if I want to introduce my hyperparameters into here, not just the parameter of interest, sigma squared, but the hyperparameters including V and S0 squared. So, right, so the case is like this. So SP squared follows some distribution, depends on, okay, so I should say it, some distribution depends on sigma squared, or I should make it here. Okay, that's better. Okay, so I'm still using that same D. And before that, I have sigma squared follows that inverse chi-square v s0 square. I have that. So those two parameters, I want to include them into the likelihood. So it's possible to maximize the likelihood and estimate them. Okay, so one way to do this is that I can first write the joint likelihood, which is let's see, we put the V here, we put the S here. Okay, so let me see. Sorry, maybe no, this is a bad way of saying it. My bad. So forget about this. So let's say that this is the density, right? But let's say what we want is the likelihood of the hyperparameters. So V and S0 squared, they should be there, okay? But how do we introduce that? So this should be defined as the data, again, SP squared density, given the hyperparameters. So I need to find a way to write down this density. But this is something not straightforward because I only know what's the density of SP squared conditional on sigma squared. And I also know what's the prior density of sigma squared. But I can do it. So in other words, this can be written as, this is what we call the very important trick of called marginalization by integration. So that means if I can write this as a first joint density of SP squared and sigma squared, they are jointly conditional on V and S0 squared, and I integrate out the sigma squared. Say sigma squared is non-negative, I do this, then the sigma squared can be gone. Right? So this idea is similar to if I wrote down here, like if I want to say the marginal density of X, right? I can do the integration of the joint density of X and Y dy, right? I integrate all the other variables, I'm left with the density of one variable. So that's exactly the fact I'm using here. And then for the joint density, it's nice because I can factorize it. I can write it as the density of SP squared given sigma squared times the density of sigma squared given the two hyperparameters V and S0 squared. Okay, this is from my likelihood. This is from my prior. So then it becomes just an integration problem. So ignoring all the technicality, assuming that you can get this marginal likelihood of the hyperparameters, just the V and S0 squared. So then empirical Bayes, what it will do is to find the maximizer of this function as the estimate. So we will say we'll put V hat as 0 square hat. This will be the maximizer of this. So basically I want to find all possible values, the pairs, such that this is maximized. And then I will take those two values into my prior. Okay, with those two values known, I go back to here. I go back to my estimator. So here the V will become V hat and S0 squared will become this S0 square hat. So that concludes the whole story. So this is the whole empirical Bayes idea, which means that you integrate out all the intermediate parameters like the sigma square here, and you only kept the parameters, the hyperparameters you need to specify in the prior. And once you get to that point, it's just the density of your data given the hyperparameters, then you call this the hyperparameters likelihood and you maximize it and find the hyperparameter values. That's the empirical Bayes. So no matter how complicated the procedure may seem, but the essence is this. So you can imagine that there might be a lot of computation needed, especially that like this integration. It may not be easily done, right? So that's why the whole field Bayesian statistics require a lot of computation techniques. And we will talk about MCMC in the last part of this lecture briefly. So as you can see, that's one technique that has been most widely used for drawing sample from the posterior distribution. So that's the case when the posterior is very hard to obtain in an analytical form. Unlike here, because we are using the conjugate prior, so the posterior has a nice form. We know the analytical formula, we know the mean, but that's not usually the case. In many cases, if you don't want to restrict your prior to be conjugate, then the posterior may get very complicated. You cannot get an analytical form. But still, you want to draw sample from it so that based on the sample, you can use Monte Carlo method like averaging to estimate, to approximate the posterior mean. So that's why MCMC is a useful technique for drawing samples from the posterior. And that will be the last part of this lecture. So I have to say that this part, this Bayesian part, maybe not too straightforward if you haven't taken some preliminary courses before. Like if you're not familiar with Bayesian, or if you're not familiar with MLE, this might be too much, at least for now. But at least I want to give you the high level idea about what it's actually doing. So those concepts will be the key for take home. One is the likelihood, one is the prior, one is the posterior. And then we want to use the posterior mean as the new estimator. So the posterior mean is this one. Why is it a reasonable estimator? It's because it's our new belief in the parameter value. After seeing the data, we update our belief to be like this, not just the prior, right? The prior belief is just this, but with our data, we update it to be here. So, and the rough way of saying that is this estimator is a weighted sum of the estimator without prior, that's the frequentist estimator, and the prior mean. So together we get a posterior mean. Okay, so that's all I want to say for today. And we will assign the first homework, I think this week. So, and it will be due in 2 weeks. So you should have enough time to work on the homework problems, but still, it's always good to start early. Okay, so that's all I want to say. Do we have questions for today's lecture or anything else? All right, so if not, then we'll see you next week. Bye.
Thank you.
Bye-bye.
Bye.
Bye.
Thank you.
Thanks.
Thank you.
Bye.